There we go. So for diazotization, you can use aryl nitration to install the nitro group. You can reduce the nitro group using hydrogen and palladium on carbon to the corresponding aniline. And then there's interesting chemistry that allows you to convert the aniline into something else entirely. And that is this molecule, which we're going to call a diazonium salt. And we will use the diazonium salt in subsequent steps in two different types of reactions as an electrophile. So we'll talk just briefly about what this step does, and then we'll talk about the properties of this molecule. Let me say at the outset, students always want to know, is the diazonium group an electron donating or a withdrawing group? Is it an ortho or paradirector? And we don't worry about that because the diazonium salt is relatively unstable. People generally don't isolate it, and it tends to decompose at greater than 0 C. So it's used as a synthetic intermediate, but generally you don't do electrophilic aromatic substitution reactions on it because it's an electrophile, not a nucleophile. So you don't need to worry about whether the diazonium group is an ortho and paradirector. Later on, when we synthesize azo compounds, you'll see that we'll do all of the electrophilic aromatic substitution reactions first, then we'll make the diazonium salt and do synthesis. So we'll have some examples of that later. The mechanism, whoops, I don't want to turn on the microphone there. Oh, and are we recording audio? Yes, we're good to go. The mechanism for this reaction is known. Sometimes I feel like seeing the mechanism is a good way to remember how a reaction happens, so I'll show it to you briefly. The NO2 ion let's see, here's the aniline. So the NO2 anion looks like this. And then, so that's sodium nitrite, that's NO2, okay? And then you're using HCl. So one of the things HCl does is it protonates the negatively charged oxygen, and if it protonates it again, you turn the water into a good leaving group, and then lone pair electrons on the oxygen can kick down and kick off water as a leaving group, and that generates the following electrophile. And this electrophile is called the nitrosonium ion. And it has a resonance structure, even though we've got one of these resonance structures where the positive charge is on the oxygen. Oxygen's more electronegative than nitrogen, so it also seems reasonable that this resonance structure should be a major contributor, and it is. So what happens next is that the lone pair electrons on the aniline nitrogen will attack the nitrogen of the nitrosonium ion, making a new nitrogen-nitrogen bond, all right? So here's what we've got. And then Cl minus will act as a base to deprotonate the aniline. And then you've got this intermediate that's called an N-nitrosamine, meaning you've got an NO group, a nitroso group, on the nitrogen of aniline. Now the reaction doesn't stop there. because as you see, we need to get all the way to the diazonium salt. And what happens is basically a series of proton transfer steps that are going to make this reaction happen. So, for example, in the presence of, and I just need a little bit more space, because we've got HCl present, we'll do some things that are similar to carbonyl chemistry. Lone pair electrons on the oxygen pick up a proton from HCl, and that should polarize the nitrogen-oxygen pi bond, and it makes it possible for Cl minus to come back in, remove this proton, and do sort of an elimination reaction, or really it's a tautomerization reaction, where now the pi bond is between the two nitrogens. And if you're looking at what we need to accomplish to get to that aryl diazonium salt, we need a nitrogen-nitrogen triple bond, right? You can sort of see where we're going now that we've made the nitrogen-nitrogen double bond. If HCl protonates this oxygen on this intermediate, thereby turning it into a good leaving group, then the lone pair electrons on the nitrogen can act as a kicker-offer to kick off the leaving group. And then that's what gives us this, what we've called our aryl diazonium salt, and Cl minus is the counter ion. Yeah?
In the kind of second step with the nitrogen, would we not expect that those nitrogen lone pairs would be more basic than the oxygen lone pair? Why don't they grab that?
So it's a good question. There's lone pairs on nitrogens instead of the oxygens. What you're proposing are reasonable proton transfer equilibria that are probably happening. This is the one that leads to the product. Yep. Okay, what else? All right, so let's talk now about what we can do with aryl diazonium salts. So, what are aryl diazonium salts good for anyway? And the answer is they are electrophiles in a new kind of reaction that you haven't seen before. And we're going to call this nucleophilic aromatic substitution. You've seen electrophilic aromatic substitution where the benzene ring was acting as a nucleophile. Now you're going to see a mechanism where a reaction where the benzene ring is an electrophile. And to see that this is an electrophile, first you need to notice that in the aryl diazonium salt, what you've got is N2, or nitrogen. Now, nitrogen is an exceedingly good leaving group. How do you know that? Because 70% of the air you breathe is nitrogen, and it does nothing to you, right? It just sits there. It's highly stable, okay? And in fact, turning that nitrogen into anything other than nitrogen gas is really difficult. It used to be that in order to get ammonia to do fertilizer, you had to, there weren't that many things that produced ammonia. Now we have a chemical process called the Haber-Bosch process that reduces nitrogen to ammonia, and that's why there can be 8 billion people on the planet. But otherwise, nothing really happens to nitrogen unless there's lightning or certain kinds of bacteria that can fix nitrogen. So it's an exceedingly good leaving group. So what we're going to do is something that's really sort of different than you've seen before. If we add a nucleophile like OH minus, we can do a substitution reaction like this and N2 is the leaving group. Now, importantly, the mechanism is not SN2. The reason it's not SN2 is that SN2 requires backside attack of the nucleophile on the sigma star, that's the antibonding orbital that's associated with the sigma bond to the leaving group. And if you know anything about molecular geometry, you know that benzene is planar. So the sigma star for this leaving group would be right inside the benzene ring, and there's no way for the nucleophile to get there. So you can't do SN2. Instead, what's going to happen is an addition and then an elimination. So what's going to happen is sort of similar to what you saw for carbonyl chemistry. The idea is that the negatively charged nucleophile is going to attack the carbon where the leaving group is, and then we're going to break that pi bond and move it onto an adjacent atom. This reaction doesn't normally seem reasonable, but the thing that drives it forward is the fact that the leaving group is so good. So let's draw that intermediate. The intermediate has nitrogen and OH on the same carbons, and then here is a negatively charged, here's the negatively charged carbon. You can see that we've destroyed aromaticity, but the anion is resonance stabilized, so that's our addition step. The elimination step is going to restore aromaticity. It's very fast, and you can see that by having the electrons on the adjacent carbon kick down and kick off the nitrogen leaving group, we easily restore aromaticity, and we get to a place where the OH nucleophile has replaced the nitrogen leaving group. Okay? So that's a new mechanism. It's called nucleophilic aromatic substitution. Turns out there are other benzene rings that do this as well, generally benzene rings that are electron poor and have good leaving groups on them. We're not going to talk about many other examples of that. They are important in industry, but we don't really have a lot of time for them. So this is going to be the one example, or this class of reactions is the one example of a nucleophilic aromatic substitution. So you can mix and match your nucleophiles. So many of the things you might imagine work pretty well in this reaction. For example, we've never known how to put an OH group on a benzene ring before. We just learned. And an OH group on a benzene ring, that molecule is called phenol. Not phenol, though some biochemists call it phenol, but we organic chemists sort of chuckle to ourselves about it because any organic chemist knows it's called phenol. It's a dialect thing, so sorry. All right, let's talk about other nucleophiles you can use with aryl diazonium salts to generate things. And some of these are going to be things you could have generated via other methods. You'll see, though, that this approach allows you to do some things that you couldn't do otherwise. So, for example, you can use copper chloride or copper bromide. I don't know what the copper is for. I don't know whether it's required for the reaction, whether it makes the reaction go better or not. But that's the reagent of choice, copper chloride. This reagent is called, the reaction is, you don't need to know this, but you may encounter it at some point in the future. It's called the Sandmeyer reaction, and it's just replacing the diazonium group with the chloro or the bromo. Okay, so that's one way, a new way to put a halide on the ring. You, of course, have done that before through direct aryl halogenation that we learned in Chapter 20. This is an alternative method, and there may be times where using this gets you the right regioselectivity, whereas the other way would not. We can do some things with this method that we couldn't do otherwise. What if you wanted to put an iodo group on the benzene ring? And the idea there is we didn't really have an iodine-based electrophile for doing aryl iodination, but You can do it using either potassium or sodium iodide, where potassium or sodium are the counter ions, and that will take this same aryl diazonium salt starting material and give you the corresponding aryl iodide. So now you can put iodine on rings. What about fluorine? Everybody wants to know, okay, what about fluorine? Well, this reagent is going to frustrate you. It's going to be one we're not going to know the mechanism for, and you're probably just going to have to memorize it. And that is to use hydrofluoroboric acid. If you want to know what that looks like, tetrafluoroborate is this, and then the hydrogen would be on one of the fluorines. Somehow, I don't necessarily know I really don't actually know the arrow pushing myself, but somehow that allows fluorine to be a nucleophile and replace the N2. Gonna be frustrated by that? I don't know how it works, sorry. Somebody probably does. I'm guessing if I don't care, most of you don't. But if you do, you can look it up, so. Okay, here's one that will be useful to you in a synthesis, but somewhat frustrating to you. You can use copper cyanide. Now, why is copper the counter ion? I don't know. Do I care that you remember it? Not particularly, though I do want you to know that you can use Cn- as a nucleophile to replace the leaving group of the N2 to generate this aryl nitrile. Now that seems obvious. Why is that cool? Well, compared to the other ones, that one made a carbon-carbon bond. And those are useful. The other reasons that this molecule, which is called benzonitrile, is useful is because it can be an intermediate to other types of molecules. So I'm going to put an asterisk on that because we're just going to review briefly to help you with some problems in the problem set and study guide for things you can do with nitriles. This will be a review of stuff that we've seen before. I told you that we weren't going to know the mechanism for it, but that it might come back in the future in synthesis questions, and I'll remind you of that. In just a minute. The last reaction that we want to talk about is perhaps the weirdest. This is going to be kind of like the hydrofluoroboric acid one, where we're not necessarily going to understand the mechanism. H3PO2, hypophosphorus acid. You don't need to know that name. This is weird because this is a reduction reaction. And this will actually replace the nitrogen with a hydride nucleophile from hypophosphorus acid. If you want to know what that looks like, I think that's right. I could be wrong on that structure. It may be something like that. Okay, so you can think of this as, we're not going to worry about the mechanism, but you can think of this perhaps as a hydride delivery reagent. You could imagine that electrons on the oxygen could potentially kick down and cause a hydride to be kicked off and delivered as a nucleophile. I'm not going to test you on that mechanism. I don't care if you understand it. It is a reduction, and you can think of this reagent as a hydride delivery reagent. We're not going to use it for anything else other than this. And you would be totally right to say that is the most useless reaction I have ever seen in the world, because if you scroll way back up, we started with benzene. And if you make the diazonium salt, what on earth would possess you to go back to benzene, unless you wanted to come full circle and just waste a lot of money? It turns out your text likes to do this because your text likes to challenge you with synthesis. And this method allows you to do some cute things that you could not do otherwise. All right? Let me give you an example of a cute thing you could not do otherwise. Imagine you wanted to make this molecule where all the bromos are meta to each other. I don't know why you want to make that, but suppose you liked making things that had that kind of symmetry and it just felt right to you and you didn't want to get the ortho or the para substitution pattern. You can't do aryl halogenation because the bromo itself is an ortho and para director. So here's the strategy. You use aniline and you do aryl bromination. Now, one of the things that we glossed over in chapter 20 that I'm still not going to hold you responsible for is the idea that aniline is so nucleophilic that when you use a Lewis acid with BR2, you tend to get over halogenation. That is, the reaction doesn't stop with just one halide at the ortho or para positions, but you end up modifying all the ortho and para positions. Now that's a minor detail from chapter 20 that we glossed over. Again, I'm not going to hold you responsible for it, but you see that it's useful here because the aniline is this strong electron donating group. It's a strong ortho and para director that places the bromos ortho and para to the aniline. And now you can see what we're going to do. This strategy of diazotization and reduction with hypophosphorus acid is going to remove the aniline directing group, and it's going to be traceless. It's going to look like it was never there to begin with. And the only evidence that it was ever there to begin with is the fact that the bromo groups are all meta to each other. So you would use sodium nitrite and HCl to put to get the aryl diazonium ion. And then you would use H3PO2 to make this. And that puts the hydrogen from hypophosphorus acid onto the ring. Okay, so useful for that one thing, kind of cute. There are some problems in your study guide where you may have to do this kind of thing. I'll give you just one example. I don't want to belabor the point because there's some other things that we really need to talk about. But as an example, your text says in problem 22.62a, make this. And there are ways you could make this without the method I just showed you. But in this particular problem, they tell you, we want you to start with aniline. Okay, so the idea is, I see that the bromo and the methyl are meta to each other. I have this idea that I need a stronger directing group, perhaps one that could, if we put it here, in other words, I can imagine that if I had a stronger directing group there, the bromo and the methyl would have been ortho and para to that directing group, and then I can remove it, okay? So just real briefly, to make the point, I'm gonna just try to keep the rings in the correct orientation. How would you install a bromo group? How would you install a methyl group? By the Friedel-Crafts reaction for the methyl group. But wait, Friedel-Crafts doesn't work well with anilines because they bind the Lewis acid catalyst. So the strategy is to use acylation chemistry to decrease the nucleophilicity of the aniline lone pair. Once you've done that, you can then do the bromination reaction without fear of over-alkylation. We're going to use the intermediate that we want where the bromo is on the orthocarbon, but you would also get the para isomer. Then at that point, you can do the Friedel-Crafts reaction with CH3Cl. And at this point, you've got opposing preferences, right? The aniline that's the amide prefers ortho and para substitution. The bromo group prefers things that are ortho and para to it. The strongest donor, which is the nitrogen, wins. So you could expect to get here without too much trouble. That then sets the regioselectivity. Now, you tell me sort of in words, what do you think I have to do to get here? What do I need to do to the nitrogen before I can do the diazotization? Got to lose the amide, right? That's amide hydrolysis. So I'm not going to draw those intermediates. We'll just put 1 using OH minus and water and heat. That's amide hydrolysis. Difficult to do, but possible. Second, we would do the diazotization to convert it into the diazonium ion. Third, we would use the hypophosphorus acid. And then in place of that nitrogen, we have a hydrogen. It looks like it was never there in the first place. This is the assassin policing is brass, meaning picking up the shell casings, or this is the covering your tracks strategy in synthesis. Not the most important thing, but I wanted you to see it because it's been confusing to students in the past. Real briefly, I want to just remind you of things we can do to nitriles. And I'm going to just tell you to see let's see, what page is this in your text? Page 724 in chapter 15. I'll illustrate one of the things you can do with nitriles, and that is hydrolysis using either strongly acidic or basic conditions that will convert the nitrile, which has a carbon-nitrogen triple bond, into something that still has 3 bonds with a heteroatom, but is now a carboxylic acid. So we don't have time to review this, but I'm just going to point you, there are other reactions as well for converting nitriles into useful functional groups. Maybe if you're doing problems and you're like, how do I get that carboxylic acid there? Think about the nitrile and give that a try, okay? Again, not the most important chemistry, but I do want you to do problems for this chapter for practice, and you may need to use some of those as resources. Okay, questions so far? All right, let's now make some dye molecules. The second big thing that aryl diazonium salts can do is they can be electrophiles for other nucleophilic benzene rings. In electrophilic aromatic substitution reactions. So let me give you an example. Here is an aryl diazonium salt. Cl minus is the counter ion. And I've already told you in the chemistry above, you've seen that the electrophile is electrophilic at the carbon that's bonded to the nitrogen. But aryl diazonium salts are also electrophilic at this nitrogen. That makes a little bit of sense because that nitrogen is attached to a positively charged nitrogen. If you had a nucleophile attack it, you could break this pi bond and move it onto that nitrogen, and then it would be neutral. So aryl diazonium salts are electrophilic at 2 places. One is the carbon. If a nucleophile attacks here, you're going to get substitution chemistry. One is the nitrogen. If the nucleophile attacks here, you're going to get addition chemistry. And the nucleophiles that add at the nitrogen are other benzene rings. So here is a benzene ring. It's a dimethyl aniline. This group on the benzene ring is an ortho-para director. So you would predict that it's going to want to attack the electrophile using either its ortho or para carbons. Let's draw the para product. We'll have electrons from this pi bond attack the nitrogen and break the nitrogen-nitrogen pi bond. What we're doing here is exactly the same as the electrophilic aromatic substitution reactions that you've done previously. The only difference is you've never seen the diazonium act as an electrophile before. Once the electrons from one of the nitrogen-nitrogen pi bonds moves out onto the nitrogen changes its hybridization. The geometry is no longer sp hybridized, but sp2, and you get this sort of geometry. On the other side, here is a hydrogen. We've destroyed aromaticity. There's a positive charge on this carbon. That positive charge is stabilized by resonance with lone pairs on the aniline directing group. And then in a final step, a base, probably some counter ion, perhaps Cl minus, acts as a base to remove the proton, do the elimination step, and that then gives you something that looks similar to the molecules that we've seen before. This is called an azo compound. Okay, so that's the other thing that aryl diazonium ions can do. I call this an azo coupling reaction. And this is a way to make azo type dyes. And you can see how you could mix and match to do this. So I want to take a little bit of time now that you've seen that chemistry, and I'm going to draw an azo molecule, and we're going to try to come up with a synthesis of it. And then you're going to need to practice this. In practice, it's not that hard. You just need to have done it a couple of times. So supposing your target is this. It's an azo compound. And supposing you want a nitro group here, and you want, I'm going to make this even more bad, a methoxy group here. Note that in an so our strategy, our key strategy, is going to be to make the azo compound from a diazonium salt electrophile on one side, and then the bond between the nitrogen and the other benzene ring is going to come from a benzene nucleophile on the other side. So if you have a choice, it's best to choose for your nucleophile the benzene ring that is more electron rich, or that has more electron donating groups on it. So which of those do you think would be best here? Which of the two rings? The one on the right? See, I got that wrong the first time every time. That is not my right, that is my left. One on the left? Maybe my brain is the enantiomer. No, sorry, enantiomer. Okay, sorry. Which ring is more electron rich, left or right? Left, right, because the donating group. So left, correct, because of the donating group. So yeah, because this has an electron donating group, probably this side should be the nucleophile. Probably this side should be the diazonium salt. So let's think backwards. In synthesis, it's often better, instead of starting at the beginning, to start at the end and work your way backwards. So the starting materials would therefore be this nucleophile, right? and then this electrophile with the nitro group here, and then the diazonium group here. So now that you've done that, you now have two different synthesis problems, which have become simpler and easier to get to. We'll start with the methoxy group. How am I going to get that methoxy group on a benzene ring? And I should have told you, yeah, your starting material is going to be benzene. Because we're assuming that you're on a deserted island, you have a fully stocked lab with any type of organic molecule that you want. You're never getting off the island and you're bored, so you're just going to start making stuff. All right? This is your nightmare scenario. All right, so how do I get the methoxy group on the benzene ring from benzene? And to do this, you want to start thinking, okay, do I know any electrophilic aromatic substitutions that put oxygen on the ring? No. But I just learned something today. I just learned that if I make a diazonium ion out of benzene, I can put an OH group there. And then I know how to put methyl groups on OH groups. That's just 351 SN2 type chemistry. So, for example, you could say, all right, we could get the methoxy group from the phenol using SN2 chemistry with some kind of alkyl halide, right? And we could get the phenol using hydroxide from the previous diazonium ion, and we could get that from benzene if we do this reaction series, nitration, then reduction to the aniline, and then that diazotization reaction with sodium nitrite and HCl. I'm going to leave that to you to work out in the forward direction, confirm that it works, but does that make sense strategically? New tools that you're going to want to practice with. The other side is a little bit more tricky. So let's think backwards. What would the diazonium group have been prior to the diazotization? We get the diazonium group from sodium nitrite and HCl, but what's the starting material for that reaction? Let's scroll back. This is something that you want to work on because a lot of people are good at predict the products. People sometimes not so good at, here is the product, and I remember the reagent, but I can't remember what the starting material was. So you want to practice your reactions in that direction as well. Scrolling all the way back up to the beginning, the starting material for a diazonium salt was the aniline, the NH2 group. So if you're thinking backwards, what would have been in place of that diazonium group would have been the NH2. Okay. At what stage do you think I want to make the aniline? Do I want to make that before or after I put the nitro group on? Probably before, right? Because remember, the aniline is going to come from a nitro group originally. So if you're not careful, you might end up proposing some intermediate that looks like this with two nitro groups. And then you got yourself a selectivity problem. How can I do the reduction and just reduce one and not the other? Probably that's not going to be efficient. Probably there was a better way. So to avoid that, what we'll do is say, okay, let's do the nitration in the presence of the aniline, and we can check ourselves and say, hey, is that going to work to put the nitro on the right carbon? And you can practice this in the forward direction. What if that aniline's there? It's an ortho and para director. If we do the aryl nitration reaction from chapter 20, will that put the nitro group? Yeah, it'll put it in the right place on the ortho carbon. So you can check the regioselectivity along the way. And then again, where do we get the aniline from? Well, we've done that before, and we learned that in chapter 20. That's just nitration followed by reduction with hydrogen and palladium on carbon. Okay? So same starting material. This is what we call a convergent synthesis because you take two different parts, you make the parts individually, and then the syntheses converge in a late step when you bring the two parts together. Just to give you a sense for strategy, I want you to think about why it would be better to do that than to do something like this, which would be to make the azo compound first and then try to modify the ring. What's wrong with that approach? Why can't I just try to get the methoxy on this side and the nitro on that side? No selectivity. The benzene rings are identical, and so you can't probably very successfully modify one versus the other. It also gives you a quandary because then you're suddenly wondering, is that azo group a donating group versus a withdrawing group? How do I control regioselectivity? Your text doesn't say, I don't know what the data are, and frankly, if we don't know what the data are, it could be that people haven't bothered to do the experiment because there would be no way to modify one benzene ring versus the other. Okay, azo compounds are kind of interesting. They're useful as dyes. Maybe in the last couple of minutes, that's sort of it for the synthesis. I will just tell you the brief story of sulfa drugs. So in 1935, there was a physician who worked at a dye factory who used a synthetic dye to kill bacteria. And you can see why he would want to do that, because people had already now, for many years at this point, been using dyes to try to kill parasites. So the dye he used was this one, and it is an azo compound. And it worked, but not for the reason he thought. And this is something that's sometimes true for drugs. The dye was called Prontosil, and what he did, it turns out he was in the situation where his daughter had streptococcal infection. There weren't antibiotics to treat that at that point, and so she was near death. In desperation, I think he brings this dye home and uses it on her because they had seen it inhibit bacterial growth in mice. So today we would consider this highly unethical. You would never test a molecule on a loved one. Nevertheless, she was near death, so what was he going to do? Turns out she recovered, and he won the Nobel Prize. But what actually happened in biology is the drug was metabolized to something. The drug itself was not active, but it was metabolized to something like this. And this was the active antibacterial agent. This is called sulfanilamide. And this led to the development of a whole host of antibiotics that are called sulfa drugs, which sort of revolutionized medicine just about the time World War II started. Many people lived when they otherwise would have died because of infections. Okay, that's it for today. I will see you next week.